In a closed room or in a packed room with no fan and no AC, if you are thinking that all the air molecules are stationary, then it is not the case, my dear friends. Then what is the case? Let's see here. Welcome, my dear students, to topic 13.4, Kinetic Theory of Ideal Gas. Now here first you have to understand something about the gas molecules. See, gas is a collection of large amount of molecules having incessant random motion. Incessant means continuous but random motion. At ordinary pressure and temperature, average distance between molecules is 10 times than the size of a molecule. Due to this incessant motion, these molecules collides against each other and with the walls of the container. See this figure here. Here is a container and these are all the gas molecules. These molecules are very large in number. Means it is almost 6.02 into 10 raised to 23 in just 22.4 liter of volume. Now do you understand what is 22.4 liter? It is just a size of one bucket, an ordinary bucket. A bucket is having a volume of nearly 20 liter. So that size contains nearly 10 raised to 23 of molecules. So you can understand how many molecules will be there in the room where you are sitting. Can you assume that? It is too large. Okay. So now these molecules are having random motion and that too a continuous motion. Due to this motion, obviously they will continuously collide with each other as well as they will continuously collide with the walls of the container. Alright. Now these collisions are elastic in nature. This is very important. Let me underline this. This collision is elastic. So total momentum and total kinetic energy is conserved. This is also important. Momentum and kinetic energy both are conserved. You know that in elastic collision, conservation of momentum and conservation of kinetic energy takes place. Okay. Now let us see topic 13.4.1, that is pressure of an ideal gas. Up to now you would be knowing just that pressure is force upon area. But how exactly pressure works in case of gas which is filled in a container, that we are going to understand here. Let us see. Consider a gas enclosed in a cube of side L. See the figure. Here is a cube having sides L and some gas is there inside this container. A molecule with velocity Vx, Vy, Vz collides with a wall parallel to YZ plane of area A is equal to L square. Now first of all look here, this is x axis, this is y axis and this is z axis. So obviously this becomes YZ plane and this becomes a plane which is parallel to YZ. Okay. So what is the case here? That you have to consider a molecule having velocity Vx, Vy, Vz. That means the components of the velocity is Vx, Vy and Vz. So this molecule with this velocity collides with a wall which is parallel to YZ plane and it is having area obviously A is equal to L square. So here is the plane which is parallel to YZ plane and this is the molecule which is colliding on this wall with a velocity Vx, Vy and Vz. Since the collision is elastic, the velocity of the molecule after collision will become minus Vx plus Vy plus Vz. Try to understand this. When the molecule will collide on this wall, it will bounce back in this direction. So obviously the x component of velocity will change. Not only that, because the collision is elastic, so the x component will remain same in magnitude, only the direction will change. That's why the new velocity after collision will become minus Vx plus Vy and plus Vz. Mind well, here the y component of velocity and the z component of velocity will not change because this molecule is not colliding with xy plane nor it is colliding with xz plane. So the y component and z component of this velocity will not change. Now Due to this collision, the momentum of the molecule will change. Here, the change in momentum of this molecule will be equal to m delta v. We know that the change of momentum can be written as delta p, and delta p is m delta v. Here delta v means final velocity minus initial velocity. So final velocity is minus vx minus initial velocity is plus vx. So it becomes minus 2m vx. That is the change of momentum of molecule. Now, as per the conservation of momentum, we can say the same amount of momentum will be imparted to the wall but in opposite direction. Thus, the momentum imparted to the wall by one molecule will become plus 2 mvx. Right? Let me show the direction of this momentum on this wall. Here is the momentum 2 mvx towards the positive x direction. Now we are going to calculate the total number of molecules colliding on the wall in a given time interval. Alright, so that we can come to know that what is the total momentum imparted on the wall in a given time. For that, let us see this. If the distance travelled in x direction by the molecule in delta t time is delta L, then we can say that delta L is Vx delta t. Listen, if this molecule is travelling a distance of delta L in delta t time, then obviously distance is equal to velocity into time. So we can write delta L is equal to Vx delta t. Mind well, we are considering this distance in x direction only. Alright. So here we are taking the x component of velocity only. So delta L becomes Vx delta t. You will understand this concept in the next figure. Okay, let us see that. Here is the same figure again. You can see this is the distance travelled by the molecule in x direction, that is delta L, and as it is written here that the molecule starts at time t and collides on the wall at time t plus delta t. That means the time interval to travel this distance delta L is delta t. The time interval is delta t. The velocity component in x direction is Vx. That's why we have taken delta L is equal to Vx delta t. Hope now you have understood this. Okay. Let us move forward. Now the volume of the container having length delta L and area capital A, which is shown in the figure, will be delta V is equal to A delta t. Now look, the area of this plane is A and the distance here is delta L. So now if I consider this volume as delta V, mind well, this is the volume between this imaginary red plane and the final wall. I repeat, this is the volume between this imaginary plane and the final wall, that is delta V. Now here the length is delta L and the area is A, so the volume delta V becomes area into length, that means A into delta L. So we are writing delta V is equal to A into delta L. If there are total n molecules in this volume, then half of them, that means n by 2, will be going towards the wall and other half will be returning back after collision in time delta t. Now let me explain this. Suppose that in this volume, that means delta V, the total number of molecules are n. Obviously all of these molecules will be moving. Alright. Now half of them will be moving towards the wall and half of them will be returning back after colliding with the wall. That's very obvious. The whole process is continuous. No molecule is stationary. All the molecules are moving. So out of this total n number of molecules, we can say that half will be moving towards the wall and half will be coming back after colliding with the wall. And because within delta t time, any molecule can travel a distance equal to delta L, so we can say half of these molecules, that means n by 2, will collide on the wall within time delta t. Okay, so that is written here that in delta t time n by 2 molecule will collide and n by 2 will be returning back after collision. So the total momentum due to the n by 2 molecules those are colliding on the wall, the total momentum imparted on the wall in delta t time will be equal to q, and q is equal to n by 2 mvx. So here 2 will be cancelled out and we will get n mvx. Mind well, here for momentum I am taking capital Q. Basically momentum is denoted by P, but P I am going to use for pressure. That's why here for total momentum I am using Q. So capital Q is equal to n mvx, where n is the total number of molecule in this volume, m is mass of one molecule, and vx is the x component of velocity of the molecule. Now if the number density is small n, see, number density means number of molecule per unit volume, number of molecule per unit volume. Small n is equal to n upon delta v, that is obviously number of molecule per unit volume. So from this you can write that capital N is equal to small n delta v. Now I can place this value of capital N in this equation at this place. So we will get capital Q is equal to small n delta v into mvx. Thus, as I said, the total momentum on the wall capital Q will be equal to small n delta v mvx. But as we know that delta v is a delta L, so I can write delta v is equal to a delta L, and also delta L is vx delta t. So the equation becomes now capital Q is equal to n a vx delta t and mvx again. So the total momentum capital Q becomes n m vx square a delta t. Mind well, here small n is number density of molecules, small m is mass of one molecule, vx is the x component of velocity of molecule, a is the area of the wall, and delta t is the time interval within which the molecule travels a distance delta L. Now we can find out force on the wall from this total momentum, because force is equal to total momentum upon time. So Q upon delta T. So when we divide this equation by delta T, it becomes F is equal to n m vx square into A. This is the force equation. Now pressure is force upon area, you know already. So pressure P is equal to force upon area. So when we divide this equation by A, it becomes pressure P is equal to n m vx square. Again pressure P is equal to n m vx square. Here we have taken Vx, that is the x component of velocity of molecule, considering that all the molecules will be having same velocity. But in practice it is not so. In practice all the molecules in gas do not have the same velocity as Vx. So instead of Vx square we should use average of Vx square. That means average Vx square. So the pressure equation now becomes P is equal to n m average Vx square. See, in practice all the molecule will have different velocity. So we should take rather an average value. So instead of Vx square we should take average of Vx square. Mind well, here I am not going to take average of Vx and then square. I am rather taking average of Vx square itself. Because see, this x component of velocity can have negative value as well, because some of the molecule would be moving in negative x direction and would be colliding in the opposite wall. Alright, that also create pressure. So if I take average of Vx, then few molecules would be having positive Vx and other would be having negative Vx. So if I take average of Vx, then the answer will become 0. Alright. So we should not take average of Vx and then square, rather we should take Vx square and then average. Because here when we take Vx square, So Vx square becomes positive for all the molecules. Whether the molecule was having negative Vx or positive Vx, Vx square will be obviously positive, and then we can take the average value of it. So finally the pressure becomes Nm Vx square. Now let us move forward. Here we have to consider one another important point. See, the gas is isotropic. So by symmetry, velocity in all the directions, that means x, y, z, all the direction will be same. So we can write that Vx is equal to Vy is equal to Vz. Look, gas is isotropic, that means its property is same in all the direction, that is known as isotropic. So when the property is same in all the direction, it's very obvious that the velocity of molecules in all the direction would be same. That's why Vx, Vy and Vz will be same. Now if the speed of molecule is v, then we can write v square is equal to vx square plus vy square plus vz square. Listen, if the resultant vector is v, then we can write vector v is equal to vector vx caret I plus vy caret j plus vz caret k. And from that you know already that we can write v square is equal to vx square plus vy square plus vz square. So here v becomes the magnitude of velocity, or you can say it is speed of molecule. So the square of speed of molecule v square will become vx square plus vy square plus vz square. But because vx, vy, vz are same, you can also write that v square is equal to 3 vx square, and then you can also take average of it. So average of v square is equal to 3 average of vx square. Now from that I can write that average of vx square is 1 by 3 average of v square. Alright. So now this value of average vx square I can place here in the equation of pressure. So now pressure will become Nm 1 by 3 average of v square. Thus the pressure on any wall of the container is P is equal to 1 by 3 Nm average v square. Mind well, here N is the number density of molecule, M is the mass of molecule, and V is the speed of molecule. Alright. Now this is a very important equation. This equation clearly shows that pressure on any wall of container is due to motion of molecule. Here V is the speed that shows motion of the molecule. Suppose the speed is 0, so there is no motion of molecule, then there will be no pressure as well. Yes, if there is no speed of the molecule, that means if the molecule is not moving at all, then there will be no pressure on the wall, that means there will be no pressure in the container. Alright. One more thing here you should note, that the pressure does not depend on the size or shape of the container. See this equation. This equation doesn't contain anything about size or shape. That means pressure is not depending on the size of the container or say the shape of the container. It just depends on the speed of the molecule in the container. Right? Now let us see topic 13.4.2, that is kinetic interpretation of temperature. Let us see. From the above equation, that means P is equal to 1 by 3 Nm average V square, we can multiply V both the sides. So we can write PV is equal to 1 by 3 NVM average V square. Mind well, here capital V is the volume and small v is the velocity. So you get PV is equal to 2 by 3 N 1 by 2 M average V square. What I have done here? In the right side, I have multiplied 2 and divided 2. So we are getting 2 by 3 here and 1 by 2 here. Also, in the previous equation, we were having small n into V. But small n is number density. That means it is capital N upon V. So small n into capital V will become capital N. So that's why in the previous equation, At the place of small nv, now we can write capital N. Right? Why I have converted this equation in this form? Because you can see this is 1 by 2 m average V square, which is average kinetic energy of one molecule, and this is capital N, that is total number of molecule. So this term becomes total kinetic energy of all the molecules. Now let's move forward. But the total internal energy of gas having n molecules is written as capital E is equal to n into 1 by 2 average V square. Look, we know that the total internal energy of gas is nothing but the total sum of all the kinetic energy of all the molecules. That means this is total number of molecule and this is kinetic energy of one molecule. So this becomes total internal energy of the gas. So internal energy E is equal to N into 1 by 2 m average V square. Now here in this equation we are already having this term, so we can replace this term with internal energy E. So I can write PV is equal to 2 by 3 E. Now from the ideal gas equation we can write PV is equal to mu RT, but mu is N upon Na, capital N upon capital Na. N is total number of molecule and Na is Avogadro number. So PV becomes N upon Na RT. So at the place of PV, here I can write N upon Na RT. So the equation becomes N upon Na RT is equal to 2 by 3 E. From this we can write E upon N will be equal to 3 by 2 R upon Na into T. Alright. What is this E by N? It is internal energy per one molecule. It is E by N. E is the total internal energy of all the molecule and capital N is the total number of molecules. That's why E upon N becomes internal energy per one molecule. So internal energy per one molecule, or say energy per every molecule at temperature T, can be written as E by N is equal to 3 by 2 kBT. Mind well, here this kB is Boltzmann constant and we already know that Na into kB is R. So in the previous equation we were having R upon Na. So R upon Na becomes kB. That's why I have placed here kB at the place of R upon Na. Again E by N, that is the internal energy per molecule, is 3 by 2 kBT. Also from the previous equation, that is equation 1, which was E is equal to N into 1 by 2 m average V square, we can write E upon N, that will be equal to 1 by 2 m average V square. I repeat, from the equation 1 I can write E by N is equal to 1 by 2 m average V square, that will be equal to 3 by 2 kBT. Now both of these equations are very important because this first equation shows the relation of internal energy of molecule with temperature, as well as this second equation shows kinetic energy of one molecule with temperature. See that the average kinetic energy of a molecule is proportional to the absolute temperature T and not on pressure or volume or nature of the gas. This is very important. See, this equation shows that the average kinetic energy of one molecule is just depending on absolute temperature T. It is not depending on pressure. There is no pressure term. It is not depending on volume. There is no volume term either. And it is not depending on the nature of the gas. That means which gas you are choosing, what type of gas you are choosing, that is also not affecting here, because in the right side of this equation there is no term indicating the nature or type of gas. So that becomes very important, that the average kinetic energy of any molecule depends only on the temperature of the gas. Means if you take hydrogen in first container, nitrogen in second container, and let us say carbon dioxide in third container, And if you keep all of these three containers at same temperature, then mind well that every molecule of hydrogen or nitrogen or carbon dioxide, they all will be having same kinetic energy because the temperature is same. Understood? Now let us see one more important point about this equation. This equation relates a macroscopic parameter, that is temperature, with a microscopic parameter, that is kinetic energy of molecule. For that reason also this equation is very important, because this is the very first equation you might be seeing which is relating one macroscopic physical quantity with a microscopic physical quantity. See, capital T, that is temperature, is a macroscopic physical quantity, and the kinetic energy of molecule is a microscopic physical quantity, and that two are being related here. That's why also this equation is very important. Now, for a mixture of non-reactive ideal gas, the total pressure can be written as P is equal to P1 plus P2 plus up to. Alright. Suppose if you are having a mixture of gases and the gases are non-reactive, so the total pressure can be written as P is equal to P1 plus P2 plus P3, which is as per the Dalton's law of partial pressure, you know already. But we already know that for a single gas, the pressure can be written as 1 by 3 Nm average V square. So here for the first gas we can write the partial pressure P1, that will be equal to 1 by 3 N1 M1 average V square. For the second gas, the partial pressure P2 can be written as 1 by 3 N2 M2 average V square, and so on. Right? So this becomes the total pressure of the mixture. You can see here that 1 by 3 is common in all the equations. Okay. Now keeping that equation in mind, let us again remind that 1 by 2 average V square is also 3 by 2 kBt. So we can write M average V square is equal to 3 kBt. Now this we can write for any gas. That means for M1 average V1 square we can write 3 kBt. For M2 average V2 square we can write 3 kBt, and so on. That means for any gas, the term M average V square will give us 3 kBt only. So now the total pressure becomes P is equal to 1 by 3 N1 3 kBt plus 1 by 3 N2 3 kBt, and so on. So here obviously this 3 will be cancelled out, and remaining is N1 kBt plus N2 kBt plus up to, where kBt is common in all the equations. So the pressure becomes into bracket N1 plus N2 plus up to kBt. Pressure P is equal to into bracket N1 plus N2 plus up to kBt. This shows one another equation of Dalton's law of partial pressure. Here the total pressure of a mixture is depending on the number density of every gas and the temperature of the total mixture. Right? Now let us learn a new thing, that is root mean square speed, that is VRMS. Here root mean square speed is a sort of effective speed. Mind well, effective speed. I am not saying average speed. Average speed is rather little less than this effective speed. Okay. Now root mean square speed, that means it is a root of mean of square of speed, that is VRMS. I repeat, the root of mean of square of speed is VRMS. So for finding VRMS, I have to take root of mean means average of V square. See this, VRMS is root of mean of V square. Alright. So I will start from the equation which is in this left side, that is M average V square is equal to 3 kBt. M average V square is equal to 3 kBt. So from this we can write average V square is 3 kBt by M. And so now taking root both the sides, we can write root of average V square is equal to root of 3 kBT upon m. But as I said that this root of mean of V square is Vrms, so I can write here Vrms is equal to under root of 3 kBT upon m. So the Vrms, or say the effective speed of molecule, depends on temperature T as well as mass of the molecule. Now let us make some changes in this equation. You know the mole number mu can be written as n upon Na or also can be written as m upon capital M. You know that n is number of molecule, Na is Avogadro number, small m is mass of one molecule and capital M is molecular mass. Now for one molecule, obviously capital N will become 1 and so you can write small m will be m upon Na. Mind well, I am talking about one molecule, that's why capital N becomes 1. So if I take small m as subject, small m will become m upon Na. So I can place this value in this equation here. At the place of small m here, I will write capital M upon Na. So the equation of Vrms now can be written as, thus Vrms is equal to root of 3 Na kBT upon m. 3 Na kBT upon m. But you know that Na into kB is R, where R is universal gas constant. So the equation of Vrms now becomes under root of 3 RT upon m. Here also you can see that Vrms depends on the temperature as well as molecular mass of the gas. For example, if we take nitrogen gas at room temperature, then RMS speed of molecules can be calculated from this equation. Let us do that. First of all, here we are talking about nitrogen. So the molecular mass will become 28 gram per mole, or say 28 into 10 raised to minus 3 kilogram per mole. Also we are talking about room temperature, that means T is equal to 27 degrees Celsius, or say it is 300 Kelvin. Now from the above equation we can write RMS speed Vrms is under root of 3 RT upon m. So here it becomes 3 into R is 8.314 into T is 300 divided by capital M is 28 into 10 raised to minus 3. Solving this we will get under root of 2,67,236 and taking root of this we will get Vrms is equal to 516.9 meter per second. So it is almost 517 meter per second. That means every molecule in nitrogen gas at room temperature will be moving with a RMS speed of 517 meter per second. Can you believe this? 517 meter per second of speed of every molecule in nitrogen gas. Now you know that in atmosphere 78% is nitrogen. That means in the room where you are sitting, most of the gas is nitrogen, and so we can say that molecules in atmosphere are moving with a speed of 517 meter per second. This is a speed more than the speed of sound in air. The speed of sound in air is 330 meter per second, whereas here it is 517 meter per second. That means every molecule in the room where you are sitting is moving faster than the speed of sound. Can you believe this? But yes, it is true. One more thing, lighter molecules will have greater RMS speed at the same temperature. Obviously, see this equation. Here the molecular mass is in denominator. That means if the gas is having lighter molecules, that means if the molecular mass is less, then obviously Vrms will be more. For example, at the same temperature, instead of taking nitrogen, if we take hydrogen, then you know that for hydrogen molecular mass will be 2 only, right? So in that case, Vrms will become 1934 meter per second. That is almost 6 times than the speed of sound in air. Can you understand this? It is almost 2 kilometer per second. So the hydrogen molecule will be moving with a speed 2 kilometer per second in a room at a room temperature. Wonderful, isn't it? So these are all the mysteries of gas molecules, or say gas in general. I hope you have understood now that the pressure of gas is proportional to the temperature. The kinetic energy of gas molecule is proportional to the temperature. The internal energy of gas is proportional to the temperature. The speed is proportional to the root of temperature. Alright. So these are the relations of different physical quantity with temperature. So here we are relating one macroscopic quantity, that is temperature, with different microscopic quantities like internal energy of gas molecule, like kinetic energy of gas molecule, like speed of gas molecule. So all of these equations are relating macroscopic physical quantity with microscopic physical quantity of gas molecules. Alright. So students, I hope you have enjoyed this lecture today, and with this note I complete this lecture here. And as I always do, I have kept a link of PDF of this lecture in the description box. You can download the PDF and can write down the whole lecture from that PDF. Alright, Anshun Baldania signing off. Take care.